We are recording. Beautiful. Okay, so want to talk about passive transport. Passive transport. What makes something passive? Yes, ma'am. Doesn't require energy from where? The cell provides no energy. The cell provides no energy. It's free shipping. Everybody likes free shipping. Yes? Holy cow. All right. If I can move stuff around my body and it costs me nothing, that's awesome. Free shipping. That's the advantage of passive transport. So where's the energy coming from? Because really nothing's ever free. It's provided by the gradient, but what particularly is providing the energy? No enzymes. The energy comes from I'm moving substance A from point 1 to point 2. The cell's not providing the energy. What has to provide the energy? The substance, the material that's being moved is what's going to provide the energy. All right, the particles are going to provide the energy. Comes to the small particle theory. Small particle theory says that all particles are in constant random motion. They tend to travel in what type of pattern? No, not yet. Pattern. They run around in circles. What type of pattern? What's lateral? It's not a pattern. A circle's a pattern. If they go in triangles, what do? I'm a particle. They travel in straight lines until what? Boom! Collision. When I have a collision, what happens? I go off in an equal and opposite direction until it hits something else. Boom! Now it sends me off in an equal opposite direction until boom! And now I keep moving, yes? And each time we have a collision, that creates kinetic energy, which helps the particles move. Yeah? So in diffusion, you have a couple classic definitions. Diffusion movement always is in what direction? It goes from high concentration to low concentration. Same is true if you want to put in the word pressure, you want to put in the word temperature. They go from high to low. Why do things move from high concentration to low concentration? Why is it easier? What's more likely to happen in high concentration than in low concentration? More collisions. If you're in high concentration, you're much more likely to collide and change direction. If I'm a particle and I'm over here by myself, what's the odds of me randomly running into another particle? Very low. So I just continue to travel in the same direction till I hit something. Boom. Now I'm going to travel for a long time going this way before I change direction. So the odds of me moving somewhere is pretty slim. Go like I do in 9th grade. But if you put me in here with all you other particles, right? Collision, boom, hip check. Comes over, butt check, boom. Comes on over, pelvic thrust check, boom. Right over here to hip check, boom. What's happening as I'm hitting each one of you? You're also moving. I just hit him, boom. He just hit Hollis, boom. There she goes. And we start having this big reaction, boom, 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 boom. Things tend to then disperse, spread out. Yes? So it's only mainly because in high concentration, we're much more likely to run into each other than we are in low concentration. We tend to go from high to low. Same thing happens in temperature, because in higher temperatures, the molecules are moving faster, therefore they're more likely to collide. Higher pressure, the molecules again are going to be moving faster, more likely to collide, and move towards low concentration. So we're just taking basically advantage of the rules of chemistry and physics. There has to be what in order for diffusion to occur? Well, in living things, we're most interested in the movement of materials across the membrane, because we're very interested in internal versus external environments. So in the context of life, we talk about diffusion in relationship to a membrane. But in order for there to be a net movement of particles in one direction or another, you have to have what? No. You have to have unequal, something called a gradient. You have to have a concentration gradient. Right? Concentration gradient is the difference you have in the concentrations between the internal and the external environment. If there is no gradient, you're going to have no net movement. In other words, there's going to be no gain or loss. But if you have a gradient, somebody's going to gain, somebody's going to lose. Yes, no? And generally speaking, the bigger the gradient, how does that affect diffusion? Faster the rate. The bigger the diffusion, the faster the rate of diffusion. Or the bigger the gradient, the faster the rate of diffusion, at least initially. Yeah? And this will continue until what happens? You reach what's called dynamic equilibrium. What is dynamic equilibrium? What's true at equilibrium? Gradients are not necessarily equal. The gradient's balanced. What comes in is equal to what goes out, or vice versa. It is not. The common myth is it's equal concentration. No. Does not mean equal concentration. It means the same number of molecules that are leaving is equal to the same number of molecules coming in. So if you have 5 going in and 5 going out, the net result is equilibrium or no change, 0. Yes, no? Right. So this is hopefully all stuff you heard in a prior course. I would hope this would not be brand new. So if we have a cell, just to give you a visual, let's say we have something like oxygen. We'll just say these little balls are oxygen. All right. I'm just going to add some oxygen here to the environment. So based on how I'm drawing this, where's the greater concentration of oxygen? And the environment outside the cell. Lower concentrations inside the cell. So just based on numbers of collisions, I would expect more molecules to move where? In. Can there be collisions inside? Can materials move out? Yes, it's just the amount moving out. Thus, I'm going to draw it with a smaller arrow. The amount moving out is less than the amount moving in. You have a gradient. More is going in than is going out. There's a net gain of oxygen to the cell. That will continue until you are able to reach equilibrium. At that point, maybe right here we've got, for every 1 going out, we've got 5 coming in. Well, over time, that's going to go from 5-to-1 ratio down to a 4-to-2 ratio. Eventually, we're going to get to about a 3-to-3 ratio. We're now at equilibrium, because at 3 and 3, there's going to be no change. However, the body's going to do what? If we let it go to equilibrium, that cell's in trouble, because it's not going to get any more what? It's not going to gain any more oxygen, and it's going to be in trouble. So instead, what do we do in real life? As soon as that oxygen comes in, we use it. So that keeps the gradient low inside and keeps the oxygen wanting to come in. We prevent equilibrium from occurring on purpose. Yes, no? On purpose. You know, we very rarely will let things like oxygen, carbon dioxide, glucose, those types of things reach equilibrium. We don't want them to reach equilibrium. Then we're going to take and store that stuff in some manner, or we're going to give that oxygen to some other cell that needs it more desperately. Yes?
Doesn't, like, your body move towards equilibrium, at least diffusion? Like, how do they keep it?
Oh, yeah, we move towards it. But a lot of systems are designed to either use the product up or break the product down or convert the product into something else so it doesn't accumulate and reach equilibrium is the primary way that we do it. All right? So, diffusion, this is what we call simple diffusion. Now, simple diffusion is the movement of molecules through what part of the membrane? Right, between the gaps of the phospholipids. This is where molecules can move between the openings and gaps between the phospholipids. We're typically talking what type of molecules? Nonpolar and small. which fortunately happen to be things like oxygen and carbon dioxide. But non-polar and small, they move through the gaps. Free shipping doesn't cost us anything. Now, some larger molecules, or polar molecules, or charged molecules, they can also move through the membrane by diffusion, but one big difference. They have to use the protein channels. They need to use those transmembrane proteins, which create those polar openings through which we can move the molecules. Yes? And that is particularly called what type of diffusion? Facilitated diffusion. Because it needs the facilitation, the assistance of a protein in order for that to happen. On that, exactly the same. Exactly the same. High to low concentration goes with the gradient until you reach equilibrium. But again, in most cases, we're going to prevent equilibrium from ever being achieved. So, simple diffusion, facilitated diffusion. The two most basic mechanisms we use to move molecules. Facilitated diffusion, very important for things like glucose, amino acids, water. In fact, water even has a specialized channel protein called a aquaporin. And again, one of the things that makes cells different is the types of proteins that are embedded in their membrane. It's not uniform. Kidney cells have a totally different set of proteins embedded in their membrane than skin cells do, which has a totally different set of membranes embedded in its protein than muscles do. Kidney cells are going to be high in, say, aquaporins. Muscle cells are going to be high in calcium channels. Skin cells are going to be very low in both. It varies from cell to cell. It's one of the things that makes cells different.
After the cells move in and out, where do the proteins go?
No, the proteins are usually a part of the permanent structure of the membrane. And the proteins, like the phospholipids, can do some sliding around and moving within the membrane. The other big type of path of transport besides diffusion and facilitated diffusion is specifically the movement of water, which we call osmosis. Okay? And osmosis is a fairly critical piece of the puzzle. Now this stupid timer's blocking it. Oh well. So we got osmosis. Osmosis is literally the diffusion of water. Again, goes with a gradient, high to low, trying to reach equilibrium. Yeah? But in water, there's a big factor that affects the movement of water. What factor affects the movement of water? Say that again.
Non-penetrating.
Non-penetrating, which means they can't pass through the membrane easily. Solutes. Solute is a big factor in determining which way water goes. The solute is the big factor in determining which way water goes. So what are some of the most common solutes we deal with? I'm sorry? Glucose is a very common solute. Sugars. Salts is a very common solute that we have to deal with. Where that solute accumulates and where it goes totally determines what happens to the water and where the water moves. So the body has a very strong interest in all of this because basically water is your lifeblood. And where you put water and where you don't put water severely affects or can severely affect the health of your system. So the movement of water is very critical to our survival. And one of the key factors that affects the movement of water is solute. That generally picks up about 3 different scenarios. Again, what I'm about to walk through hopefully is a review of what you covered in a 9th grade course. There's sort of 3 scenarios that we can create based on water and solute. One is called isotonic, the other is called hypotonic, and the third is called hypertonic. So just dealing with the prefixes alone first, what do we mean by hypotonic? First of all, what's it even referring to? Hypo, iso, and hyper. It's not the water. It's specifically referring to the level of solutes in the external environment. It's typically referring to the solutes in the external environment, typically. Right? So you need to know what it's referencing first. It's referencing the amount of solute usually in the external environment. So what's hypo? Just the word hypo, the prefix hypo, what's that mean? Less, or we often say below. Think of like a hypodermic needle. Hypodermic needles are needles that go below the skin. Hypothermia, your body temperature drops below normal. So hypo, one way to define is below. Hyper is a more above. You know, hyperactive is a fairly familiar term to all of us. Iso approximately means same or equal. Okay? And those are the prefixes that we use to describe the situations. And what affects it is the solute. So I'm going to use S for solute. Who cares what the solute is right now? But let's say we have 10% solute inside the cell. What percent is going to be water then? 10% solute, 90% is going to be water. If this is an isotonic situation, we would expect what percentage solute outside? About 10% solute outside. And about 90% water. So which way is the water going to want to go? We're going to have as much water going out. The tendency of water to want to leave is about the same as the tendency of water to want to come back in. We would expect almost an equal exchange right from the get-go. We're already at equilibrium. Thus, iso equal. Therefore, what's the net change to the cell? 0. The cell remains the same. It's unchanged. This is the desirable state for animal cells. Animal cells prefer to be in an isotonic condition. Your body is constantly making adjustments, shifts, and changes to keep you at an isotonic state. That doesn't mean equilibrium. It's keep you in an isotonic state. If you're not in an isotonic state, we say you're out of homeostasis. You need to return homeostasis to the body. If you go to the hospital and have to have an IV put in, they don't give you distilled water. That's not an isotonic solution. Distilled water actually could kill you. Isotonic solution, that fluid in the bag at the IV bag, is actually designed to be at equilibrium with the blood. Right? So that it should help rehydrate you, not the opposite. Yes. You can be isotonic and still not be at equilibrium. On the big picture. So what's hyper? So if we go with the same scenario inside the cell, 10% solute, 90% water, that means in a hypertonic situation, what happens to the solute level outside? It has to go up. It's hyper. It's above. So let's say it jumps up to 25 units of solute. Well, what does that do to the water? The water decreases to about 75. It's a little bit of a simplification, but gives the idea. So which way does water have a stronger tendency to go? Out. It's going to have a stronger tendency to go from high to low. Some will come back in, but overall more water is leaving than coming in. The result is the cells should do what? Should shrink, should reduce in size. In plant cells, they have a hard time shrinking because of cell wall, but they can have what's called plasmolysis, where the membrane pulls away from the cell wall, which causes it to lose pressure, what we call turgor pressure, and the plant becomes very limp, weak. Yay, nay? Okay. And then we jump to the other end of the spectrum, hypotonic. Again, let's start same scenario, 10 solute and 90% water. So in this case, solute would have to be lower than 10. So just say it's 2% solute. So it's 2% solute, water is approximately 98%. So in this case, water has a greater tendency to go in. More water is going to come in than is going to go out. Therefore, there's going to be a net gain. This cell is going to swell, expand. If you gave yourself distilled water, like I said, with an IV, the problem is your red blood cells have no ability to adapt, and so the red blood cells would swell to the point that they actually would burst, rupture. Actually, plant cells prefer this. Plant cells, like I said, animal cells like isotonic environments. Plant cells love hypotonic environments because hypotonic environments allow them to maintain turgidity, turgor pressure. Allows them to be under good circumstances. So from a 9th grade level, introductory bio level, that shouldn't be anything too brand new, I hope. And maybe I had to refresh your memory, that's okay. That's about as far as we usually go 9th grade with it. So what we're going to introduce is what's called water potential. Water potential becomes a way to mathematically measure the movement of water. All right? So let's clarify a couple things first. Water potential measures the tendency of water to want to leave an area. Measures the tendency of water to want to leave an area. And it's directly related to the amount of solute. Directly related to the amount of solute that is present in the environment. Really what it comes down to is if you have, the more solute you have, the more water that's going to stick to the solute. Remember polarity and polar covalent and the attraction? So if you have a lot of solute, a lot of the water gets sort of stuck to the solute, chemically speaking. And therefore, if I'm stuck to the solute, I'm less likely to move, bounce off of other water molecules and go somewhere. So if you give me a lot of solute, the water becomes bound up. You have very little free water. Very little free water to move. If you have very little solute, most of the water is not attached to anything and it's free to move. We call that free water, free energy water. So less solute, more free water, the more likely the water is going to leave and go somewhere else. The more solute you have, the more the water is going to be bound up. The less free water you have, the less likely it is to change. Is that going anywhere? So in this scenario, over here at hypertonic, I've got 10% solute, which is going to bind up less water than 25% solute. This is going to have higher water potential because it has less solute. This is going to have lower water potential because it's got more solute. They're inversely proportional. Therefore, water always moves from high water potential to low water potential, which supports the idea that water is going to leave the cell and it's going to shrink. With me at all? Vice versa over here, I've got 10 grams of, or 10% solute to bind with water versus only 2% solute. Much less water is going to be attracted to solute out here, therefore there's higher water potential. Relatively speaking, this one has more water bound to solute, therefore less free water, less water potential, thus supporting the idea that this cell is going to gain water and increase in mass. Questions so far? So water potential, that's what this is supposed to say, but now that recorder is blocking it. Water potential can be measured. There's two equations that we're going to deal with. First equation is we represent water temperature with the Greek symbol psi. That means water potential. And water potential is affected by two variables. One is pressure potential, which we do as psi p. That's pressure potential. And that plus what we call solute potential, which is psi s. All right? So this is water potential. And this is pressure potential. And this is solute potential. Those are the two key factors that affect water potential. If you did the background reading, you should have read that under normal atmospheric conditions, sea level, normal atmospheric conditions, what is the value assigned to pressure? Open system at normal sea level. Pressure is assigned. I don't have time to wait for you people. The pressure is 0. So most of the cases we're going to be working with is 0. Only when it's a closed system or you have something that can create pressure do you have to worry about that variable. Plant cells, we have to worry about pressure because plant cells have what? Cell walls which create resistance to the expansion and shrinking of the membrane. Animal cells, typically we're not dealing with a lot of pressure potential because there's no resistance to the membrane expanding and relaxing. Okay? The other is solute potential. Well, what's the least amount of solute you can have? 0. And that would be in what type of solution? Distilled water. Distilled water has got 0 solute in it. And we assign that what value? 0. Okay. Distilled water is 0. Which means all other numbers have to be what? Above or below? All other numbers are going to be above 0 or below 0? Below. All other numbers are going to be negative. You can only get more and more negative if you keep adding solute. The more solute you add, the more negative the number becomes. The less solute you add, the closer to 0 it becomes. So the closer to 0 you are, the more water potential you have because the more free water is available. The more negative the number, that means the more solute you have, the more water that's bound up, the less water free to move, you have much less potential. Going anywhere? The other side of that is, since pressure potential usually we can ignore in most cases, there is a way to calculate solute potential directly. There's an equation that's called negative I times C times R times T. That is the equation for solute potential. Then the negative I represents what we call the ionization constant. And really what that number is how many ions does the molecule break into when it's put into water. So for example, if I put table salt, sodium chloride, into water, it breaks into how many ions? 2. So the ionization constant is 2. If I put sugar into water, how many components does sugar break into? 0. Breaks into, it doesn't dissolve. I mean, it doesn't break into ions. All right? It's a polar molecule. So since it doesn't break into anything, it remains as one single molecule. We say its ionization constant is 1. And those are the two most common ones we'll deal with are sugar and salt. You get the idea? C is the concentration, the molar concentration of the solution, which is what we were trying to figure out with the potato. And we'll come back to that, probably not till Monday. R is what's called the pressure constant. There's nothing magic about it. It's a predetermined number, which happens to be 0.0831 bars if you want to know the units. That number is always the same. And then T is for temperature, but it's temperature in degrees Kelvin. And if we recall, how do we convert from Celsius to Kelvin? We just simply add 273. So if your temperature was 23 Celsius, then add 273 to that, and it would be 296. Okay? So those are the numbers that you plug in, then you multiply them together to get your solute concentration. Then you can plug that into this formula to get your water potential. If you're dealing with animal cells under normal conditions, usually it's going to be 0 plus whatever you calculated for your solute potential. It changes with a little bit with plant cells, as you'll see. With me still? All right. This back on. So we're looking at this sheet here as a basic introduction. So we've got two open systems at atmospheric pressure. One has got sucrose in it, one has got salt in it. Let's take a look at beaker A, which has the sucrose in it. So pressure potential, what's the symbol for pressure potential? Psi P. Okay? And since we're in an open system at atmospheric pressure, that's going to be 0. And then we have an ionization constant. Sucrose is going to ionize into how many molecules? 1. That's I, and that would be 1. Because sucrose is a polar molecule, it's not going to ionize. Molar concentration is what? In this case, it's 2.5. That's what it says in the beaker, 2.5 molar sucrose. Pressure constant is a given. That's 0.0831. Temperature in this case would be what? 25 plus
78.
273, which would be 298 degrees Kelvin. So then, now that we've got all our variables identified, remember what's the equation for solute? Solute equals negative I times C times R times T. So basically, I plug in the numbers. I was 1, C was 2.5, R was 0.0831, and temperature was 298. So if I multiply those four numbers together, run through the calculator, you would get negative 61.9. Following how I'm doing it? So then I go a little bit further down. That's my solute potential. What I really want to know is my water potential. So to get my water potential, I have to go back to the first equation. Water potential, which is psi, equals pressure plus solute potential. So in this case, my pressure potential again was what? 0. And my solute potential was what? Negative 61.9. So 0 plus negative 61.9 is negative 61.9. Make some sense? All right. Go ahead and try the right side and see if you can do that. Pay attention to the fact that it is salt. So we should come up with negative 123.8. So when we look at the two, which one has the greater water potential? Which one has the number closer to 0? A. Negative 61.9 is larger than negative 123.8. So since negative 61.9 is larger, it's got more water potential. So which way would the water move, from A to B or B to A? We go from A with the larger potential to B, which has the smaller potential.